Hi, everyone. My name is Gary. I'm starting my fourth year of PhD at Stanford. I interned with Keith, Zach, and Zach last summer, where I worked on federated learning. Today, I'll be talking about some findings we made during my internship, which suggests that federated dropout may not be a silver bullet solution to scaling up model sizes. In particular, I'll begin with some motivation and background on federated dropout before jumping into our contributions and experimental observations. So recall in the standard FL setting, the model being updated on the server is the same size as the models on the client. Model size is constrained by communication cost and the smallest client's computational budget. If we think of client devices as being cell phones, we can't train a massive model in FL like we could on a remote server. Contrast this with the centralized setting. Many of the biggest breakthroughs in recent memory have come from scale. This begs the question, would we see the same trends in FL if we were able to scale up model sizes? So in an effort to answer this question, Caldas et al. Proposed federated dropout as a method of training larger models in federated learning. So federated dropout modifies the traditional premise of FL. In federated dropout, the server uses small models on the clients to train a larger server model, which is deployed on the clients after training. So a crucial assumption made is that clients are unable to backprop a big model, but is able to complete forward passes. So this assumption makes sense, for example, in convolutional neural networks, where the memory consumption of backpropagation is often much larger than the forward pass. So how exactly does federated dropout work? So I'll run through the pseudocode quickly right now. Before anything else, the server initializes a big model. Then the server shrinks the big model into a small model. So I'll discuss exactly how this shrink operation is performed later, but for now, let's treat it as a black box. In the second step, the small model is broadcasted to all of the clients. The clients then perform their local updates like they would say in federated averaging. Next, the clients then send back their local updates to the server. The server uses the client updates to generate a new big server model. So I'll describe in detail how exactly this unshrinking is done in a little bit as well. And finally, we repeat this procedure until we've converged. And after training is complete, the large model is broadcast to all the clients for inference. So what exactly is shrink and unshrink doing? So suppose we have a two-layer neural network denoted by F. A and B are weight matrices, and sigma is some activation function. The server shrinks the function F by using a projection matrix P to reduce the sizes of the matrices A and B. So in visual terms, we're using the blue matrices to shrink the green matrices into the smaller yellow form. The columns of P are comprised of standard basis vectors. This choice makes this shrink operation reminiscent of traditional dropout. So the idea being communicating the function g to clients is cheaper, and backpropagating g is also cheaper. Then later in the algorithm, once clients have returned their updated g function, the server then unshrinks the updated g back into the original size using the projection matrix P. So for a general neural network, we repeat this shrink and unshrink strategy layer by layer. So in the original federated dropout paper and many of the follow-up works, the experiments fix server model size and report how the test accuracy behaves as the client model size varies. So this plot on the screen is like a stylized summary of a best case scenario result you could probably see in one of these works. As the client model size approaches the server model size, the accuracy sometimes performs a percentage point or two better than the accuracy of the server model returned by federated averaging. So optimistically, these results suggest for some data sets, federated dropout can shrink client model sizes by about 25% for maybe 1 or 2 percentage points of improvement. Okay, moreover, there's a lot of reading between the lines here because it's not immediately clear how much better federated dropout is compared to just training the largest model you can fit on the client using federated averaging. We instead design our experiments from our first principle. Clients can only train models up to a certain size, but can evaluate larger models. Thus, in our experiments, we instead fix the client model size and report how the test accuracy behaves as the server model size varies. So this gives rise to a very natural baseline. whatever larger model we end up training using federated dropout should at least outperform a small client model trained using federated averaging. So that's like the yellow dotted line, that's the baseline. So now time for our experiments. So I'll be focusing on the EMNIS task using a convolutional neural network. We'll have 3 different model sizes denoted by small, medium, and large. For some perspective, the medium-sized model has about 16 times larger memory overhead than the small model, and the large-sized architecture has a 64 times larger memory overhead than the small model. The client model size will always be small, and we will set the server model size to be either medium or large. And our baseline is, of course, training a small-sized model via federated averaging. So just to note, steep implementation opportunity costs motivate our focus on these larger shrinkage parameters, like this 16 and 64 multiplicative factor. Federated dropout is non-trivial to implement in Google's federated learning pipeline. So really, for it to be worth implementing at scale, we need to show a large return on investment. So on to our results. In our first experiment, we vary the server model size and the hyperparameter tune each method. So in this table, we report the best test accuracies. The baseline performance is the number in the top right corner. So to put it simply, federated dropout in the first column does not beat the baseline. And we emphasize that this isn't an artifact of the baseline being too difficult to beat. We show that a very simple ensembling strategy in the second column is able to beat this baseline. And so a quick detour. In particular, this simple ensemble averaging strategy just independently trains k copies of the client-size model using federated averaging. So in the diagram here, k equals 4. And then at evaluation time, it just averages the outputs of each of the models. It's really the most basic ensembling strategy you can imagine. And so this is the main punchline of our work, but we have 2 more experiments to drive this point further. I don't have much time to get into the details, but essentially, we control the number of submodels federated dropout can select from. And our results suggest that the best performing version of federated dropout is essentially approximating the simple ensembling strategy I mentioned before. So just a note on some limitations and then some takeaways as well. So at the very least, our results indicate that federated dropout is not able to reduce the number of parameters being trained by a factor of 16 or more. Maybe this isn't terribly surprising, as it corresponds to a large dropout rate. While this does technically leave the door open for improvements of a smaller magnitude, the implementation of overhead of federated dropout in the already design-intensive federated learning pipeline, difficulties of applying federated dropout to language models, and the improved performance of a very simple strategy like ensembling suggests that pursuing more advanced ensembling ideas may be a more fruitful decision. There's been some work in federated learning which experiment with more sophisticated ensembling ideas. And given the promising results in this talk, I think there's a lot to try out there. So with that, thank you for your time.